We have great honor today to host Pietro Altermatt here. Pietro, I'm sure that everyone knows, is like the world expert in simulation. He's the standard for modeling with solar cells. Pietro worked here for 9 years, I think, until 2002 or 3. And in the last 10 years, he led the simulation group in Leibniz University in Germany. So please welcome Pietro.
Thank you, everyone, and thanks for the kind introduction. Yeah, it's a honor for me to be here and to talk to all these wonderful PhD students and other students. And I actually tailored my presentation to the students. So I will go back to the basics, but the experts will probably have new stuff towards the end of it. So let's start with the question, which parameters in a cell do influence the fill factor? And I suggest just turn to your wonderful neighbors and talk about it for about 1 minute, so you know of, your knowledge a bit how you are. Huh? I would say 1 minute. Okay. I think we can continue. So what actually influences it very strongly is, of course, the series resistance. This is what all textbooks say, and this is, of course, true. I mean, you see that even a small resistance really gives a big drop in fill factor. Huh? That's well known. What sometimes people don't always think of is that the fill factor is quite a strong function of VOC. So I took here as an example Martin Green's approximation formula. There are quite a few in the community where you see if the ideality factor is 1 and no series resistance, this is about your, say, utmost limit of the fill factor, unless you are Auger limited, then the ideality factor smaller than 1. Yeah? The next thing is the ideality factor, and this is what I want to concentrate about today. And as you see, it has a really strong influence on the fill factor. So don't forget about it. Don't forget about the ideality factor when you think of a fill factor. And eventually, you can combine the equations like this to get all these major influences in here. And there is actually a nice paper about an overview of these different analytical equations for the fill factor here, published in 1987. So it's quite an old topic, isn't it? So next question to all of you, please discuss with your neighbors. When you got a series of experiments, so if you have 10 experiments, and fill factor VOC and JSC behaves like this, have you got a fill factor problem? Do you need to address something that really affects the fill factor in improving your experiment? And you may not be able just to say yes or no, just like this, but how would you find out whether you got a fill factor problem or not, or whether you should concentrate on other stuff? Just about 1 minute again, please. Eh? Okay, so I hear yes and no and whatever from the audience. I mean, it's not quite obvious. The way I would approach it, hi Martin. The way I would approach it is I will take his formula and just try to fit the behavior with dependence of VOC. So you can do that in various ways. You can do the ideality factor 1, then you get the most top one curve. You can lower it by the ideality factor or by RS, whatever. You see, it's quite the same whether you got a series resistance or a different ideality factor. So that means, because that line, Martin's equation, fits the data, it means the fill factor drops only because VOC drops. You don't have a fill factor problem as such. Huh? You would have a fill factor problem when the data looks like this. And then you know, okay, I need to address improvements that directly relate to the fill factor. So it's advantageous to actually consider the fill factor in relation to VOC. in many experiments. So the point I would like to make today is that the ideality factor can actually influence the fill factor as much as the series resistance. And this is sometimes not thought of when people do an analysis of the fill factor. So this brings me to the contents of today. I will group it in 2 chapters. One chapter is I just talk about characterization using IV measurements, because most people of you probably don't do in-depth simulations. And the second part will be a loss analysis really with doing simulations. And then we look at the dynamics of the fill factor with simulations. So first, just the characterization. And just guide you through, like when you do online shopping and you are guided through with your credit card to pay. So I thought I'd guide you through up here of what to do to get a proper analysis of the fill factor. So people in standard measure the dark IV curve and one sun IV curve. Some measure JC-VOC curve. But I also recommend you, when you're interested in a proper analysis, to measure both an IV curve that's a bit above one sun and a bit below one sun. Often statistically, and with the error analysis, it turns out that about 10% variation is quite optimum, but it can also be more if you need more, if you need bigger differences between the sun or so. So because I tailored this presentation for students, I thought I'd shortly guide you through about logarithmic IV curves. So what I usually do when I look at an IV curve to analyze it, I shift the one sun IV curve by JSE. I learned that actually 15 years ago here in the lab. And when you shift it, ideally they would coincide, but you got series resistance losses, of course, and those reflect in the logarithmic and one JSE shifted IV curves like this. And from over here now, I take just a zoom in view, and that gives the same experimental example like this. I actually hope that you are all a bit familiar with this, but if not, I hope that helped you to guide you a bit through the kind of standard evaluation the UNSW has been doing actually for 2 or 3 decades, I guess. Huh? So what can you see? You can see that RS shifts the one sun IV curve to the left because current is flowing out of the cell, and it shifts the dark IV curve to the right because you induce current in the dark. And ideally, the JSC-VOC curve is not affected by series resistance, and that's why it actually runs at the green curve here. It runs where the ideal curve runs. So how can you actually do a good extraction of RS? This is often a problem when you analyze data from industry, because they have a fast pace and it's quite difficult to do a proper RS analysis on a fast pace, even if you got good flash testers, whatever. So sometimes you need just to take one cell out of the production and really do it in the lab and take time to analyze it. And there are a few different methods. You may heard of that, the JC-VOC method, where you just look at the differences between the green curve and the red one sun curve and say, well, the green curve is not affected by RS, so this is quite, my kind of standard. And then you get that green curve over here. This is RS as a function of the bias, and this is MPP, this is VOC. And there are also other methods like the double light level method, triple light level method. And you see at MPP there's quite a distinct difference between these methods. I mean, don't worry about how RS behaves down here. It's not important to cell analysis. Important is around MPP and between MPP and VOC. That's where it affects the fill factor. And you see, I mean, if you would zoom in, you would end up with quite a big difference. And that's why I prefer the triple light level method from Fong, McIntosh and Blakes, where you measure those 3 IV curves. The advantage of this method compared to only 2 curves, the double light level method, is that inaccuracies cancel out to zeroth order. You could also do the 5 curves, and then you would have a cancelling out of first order errors, etc. So the more curves you have, like in their paper, the more kind of small differences cancel out. And as expected, once a V curve is flat down here, you know, the linear IV curve, the series resistance shouldn't change, should it? I mean, the current path is the same between JSC and where the V curve still stays horizontal. And actually, with these improved methods, you get that kind of behavior. But as I said, important is the fill factor a little bit below MPP if you work in a module, and between MPP and VOC if you actually want to analyze the fill factor. So this brings me to the next thing. Once you got RS, what about the ideality factor? How does that connect with anything in the cell? And I better draw this. Let's say you got a cell that has a surface recombination velocity as a function of delta n, say delta n and s, and usually it goes down a bit. Depends a bit on your charge, on your electrostatic conditions, etc. But you're probably familiar that surface passivation may be injection dependent. Also bulk lifetime may be injection dependent. You've got actually quite a few sources of injection dependency in modern time PERC cells, for example. So this is quite a modern topic. So what it does is, let's say at small voltages in the logarithmic IV curve, so this is V, this is J, you got a large J naught, and at higher voltages you got a smaller J naught. And so you actually, your IV curve then bends. Say it goes along the large IV curve, large J naught, and it has a transition to the small one. And say if your MPP is whatever below here, say your MPP is here, your VOC is here, you can imagine now when you transform that back from a logarithmic scale to a linear scale, that this lowers your fill factor. So any change in recombination as a function of delta n, of injection density, which is basically as a function of external bias, gives you a lower fill factor. We will see various examples then coming up. So this is also the reason why the JSC-VOC method often underestimates RS. Why? Because a solar cell works under different illumination conditions. So here it works at illumination condition of 1 sun. Down here it's actually only 1/10 of a sun. Down here maybe a 1/100th of a sun. And because you got less light, you got a smaller delta n, you get a higher S or a lower lifetime, whatever in your base, and that changes your J naught. And so when you compare, when you extract RS from the JSC-VOC method, you got the kind of recombination behavior mingled into your analysis. And I strongly recommend you keep it cleanly separate. What's recombination and what's RS, and with that method you can't keep it separate. This is actually quite old knowledge. I just came across it when I thought what I did at UNSW 10 years ago, with Renewable, etc. So for those that simulate, you could do just a simulation, a device simulation where you have a little domain. You could do a circuit simulation to include the metal grid. You could even do a circuit simulation to model a whole module. And when you do that, you can quite easily model internal resistances, because internal resistances are quite easy to model. It's not like recombination. It just depends on your dopant profile, and you need to get the voltage right. And this is what you see here as internal resistance. Just in standard, I model that, and then I actually know what's internal resistance. That means the semiconductor part, the contact resistance part, and what's the metallization. The metallization is RS on top of here, and RS below here is internal one. So this then leads us from the measurement to a proper extraction of RS and possibly simulation of the internal one if you simulate to actually a parametrization of RS. I usually just use a normal polynomial and say V0 is often VOC because the resistance drops down towards VOC. This has various reasons. One is it's a spreading resistance. The other is the base has often more minority carry, so it gets more conductive, and that lowers the internal resistance a bit. Like in this example, you see it lowers here towards VOC. This was a 1 ohm centimeter base, but if you work with, say, 2, 3, 5 ohm centimeter, then that will drop much more there. Huh? And once you got that polynomial, you can actually display an IV curve that's properly freed of RS. And it looks like this. This experimental one, just again in logarithmic, in a logarithmic plot, looks, like this, and this is MPP here actually. And when you do a voltage-dependent RS correction of your voltage, then you get that curve. And then you can actually look at the fill factor that's extracted without any RS. Many people just take RS at VMPP. This is kind of a shortcut, but just look at it a bit more closely. The dashed curve is actually the IV curve that was extracted with just a constant RS taken at VMPP. And you see that it doesn't really display exactly what's happening internally in the cell. So I find it quite important to really correct the IV curve as a function of voltage and not just take a constant RS, unless you got a cell where RS is basically constant, independent of voltage. But I have actually rarely seen such a cell. There are quite, and often quite old cells are like this, but not the newer ones. So you also see that the extraction of the fill factor has a bit of a difference. It's not a very big difference, but still it actually depends on how you extract RS. Eh? And then you can just compare this fill factor with the fill factor taken at the ideality factor equals 1. That's often in literature called the pseudo fill factor. That's why it's spelled PFF. And the pseudo fill factor is the one, that's where you remove RS. And then you compare the pseudo fill factor, say 83.18, you compare it to Martin's equation. And then you know, okay, if I remove all the series resistance properly, I still don't have a fill factor I would expect from an ideal cell having unity ideality factor. And that gives you a feel of what's happening in the cell, how much the fill factor is influenced by recombination. This is basically the difference between PFF and unity FF, and how much it is influenced by the series resistance. Okay, so this was quite basic. I think many of you may know, but I tailored it to students, so I hope to them it's at least a good repetition if it's not new. And that brings me to the second chapter, to the actual loss analysis. Using simulations. So you're probably familiar with simulations that when you just cut a cell, that you only need to simulate in a small domain, in a symmetry element that contains all the internal features. But because it doesn't contain the metal grid, you do a SPICE simulation on top of that, where you feed in the IV curve of your single numerical simulation. And then you can actually even simulate multicrystalline cells, if you like, or any inhomogeneities or whatever. Eh? So that's quite a common approach to simulate things. And the ultimate test whether your simulations work quite well is actually when you simulate the ideality factor as a function of bias. And you see here the measured one Zand curve is yellow, and the simulated one is red. And it works fairly well if you got the right input parameters to your model. And what's a good set of input parameters we will see shortly. But this plot is quite sensitive to your input parameters. If you do anything wrong in the simulation, it will most probably show up in your ideality factor. So for me, that's an important test before I dare to tell manufacturers, okay, I analyzed your cell properly, I'm able now to make predictions of what improvements are possible in your manufacturing, for example. So these days I mainly simulate for PV companies. Okay, now to understand the analysis of cells with simulations, I like you to repeat a bit the internal behavior of a solar cell, because only if you are aware of that, you fully understand the analysis. And this is again a question to you and your neighbors. You got a solar cell in the dark, just keep it simple. With an applied bias, you inject electrons here in the N-type part of the diode. It's just a normal PN diode cell. When you apply a forward bias, and I ask you, how should you get a current through that device? I mean, is that what you may think, that the electrons go here and then they drop here at the middle? Is that a very likely current path? Or how do currents go through a dark diode or to a dark solar cell? And I would say we can spend again a minute with your neighbors on that question. Eh? Okay, I see there are lots of discussions. That's good, because it shows me that this is really kind of an open question, isn't it? I mean, before you really simulate, you can't really know for sure, but this is a very unlikely current path. And why? I mean, you usually look that there are very few electrons near to the hole contact, because otherwise you really got lots of recombinations, say at a metal contact or whatever. So usually I would say in a medium cell or better, this is a very unlikely current path. So how should the current go? I mean, you need to go from here to here. So somewhere the carriers must recombine to get there, even if they recombine at the contact. Or they may recombine by Auger or radiative, whatever. And exact proportions, this is what you do with an analysis like simulations or an analytical analysis. But you need to be aware that you can't drive a current through a dark diode without recombination. And don't worry, you will always have recombination, because you've got a semiconductor that absorbs light, and that's, the reverse process of any recombination. So it's actually that the current in the dark is equal to the recombination you have. It's a direct measure of your recombination rate. There is no factor of proportionality, or it's just unity proportionality. Huh? So when you look at in the dark again and you apply a bias, you see that the minority carrier density increases actually exponentially with lowering the barrier height across the p-n junction because of the Boltzmann factor. So the darkness of red shows you there are many electrons and just a few electrons higher up in energy. And the same actually for holes. So that because any type of recombination we usually have in solar cells is proportional to the minority carrier density, and the minority carrier densities increase exponentially with applied bias. You get an exponential increasing recombination rate with bias, and with that you get an exponentially increasing IV curve. So this is the most direct reason I find to understand why a solar cell has an IV curve like this. Okay, then when you got many defects, you got more current at a given voltage. And if you got just a few defects, say if you're shock with Hall emitted, you get very little current at a given voltage. Well, under illumination, things become a bit more difficult. And this is what I like to address here. I mean, it's quite easy to understand that instead of injecting carriers from outside, you put the carrier injection basically into the cell with illumination. So you get a surplus of carriers that leave the cell. And that means your current direction just switches direction, and with that it switches actually to negative values. And if your Fermi level stays the same in under illumination and under dark, this is so-called superposition principle, also the shape stays the same. And that's how we end up at the illuminated curves. And you directly see if you get fewer defects, you get a higher VOC, because you just shift it down. Okay, so I'm actually concentrating on that. It is that under illumination, you got in silicon solar cells a bias-independent generation. Of course, if there are any people that are busy with organic solar cells, this is not necessarily the case in these cells. But in silicon solar cells, the G is just a straight line. And the recombination is basically, if the superposition principle applies, would be just the dark current. You subtract from it plus Z off at JSC because you're not a thermal equilibrium here anymore. So that blue part is basically your recombination losses. So G minus recombination losses as a function of voltage gives you the illuminated IV curve. And this is why I still love to actually look at solar cells with my simulations by just plotting the recombination currents integrated over certain parts of the cell, like an emitter base, aluminum back surface. This is what I learned 15 years ago here in this lab. And I have tried out many other kind of ways to analyze solar cells with simulations. I always come back to this one because it gives me a direct measure of what I can improve in a cell. If I take a so-called free energy analysis, a Vega analysis, or whatever that exists out there, I'm not always sure what part of these losses I can actually reduce. But when I look at the currents, this is what drives my current through. And if I look at these recombination rates, I get a direct relation to the currents and to what I actually get out of a cell. Okay, so you see in this graph, here's the voltage, here's the recombination current. Say the emitter clearly dominates the total losses. I mean, they add up. And in this case, the base hasn't got that many losses compared to the emitter. So this cell is clearly limited by the emitter. This was the case in industry until recently, really say until maybe 3 years ago or so. This was just a normal cell in industry. And I always denote this line here as MPP and this one as VOC. So I will keep with the colors for the rest of this presentation. Okay, with this kind of basic knowledge, we can actually look at predictions we can do with simulations. So let's say you improve the emitter. And at the right, there's a cell where the emitter is improved. The base and the aluminum back surface fields, be it standard or a PERC cell, doesn't matter, are the same. You see that these current curves change quite a bit. And now you improved the emitter. That means your VOC that was limited by the emitter before is now really higher. You go from 614 to 633, which is not very high, but it's still an improvement. And your fill factor, and here we are back again to the fill factor, drops. And you think, okay, I improved the emitter by a light diffusion. And that gives me a high sheet resistivity in the emitter. So when the current flows along the emitter, it suffers from a higher potential drop, and that causes my higher fill factor. So in that case, I simulated it. That's a real life example from a few years ago. People concentrated on kind of putting the front fingers closer together so they won't have as many sheet resistance losses in the current path in the emitter. They just tried to optimize metallization and the emitter to increase the fill factor, and it didn't work. It simply didn't work. Why not? Why didn't it work? Well, in this case, it was actually the base that was the reason for it. The resistivity of the base stayed the same. It wasn't a resistive loss of the base. It was that most materials, not all materials, but quite most you buy on the market, have a fairly strong injection dependence. So here it is, after really degradation of the so-called boron-oxygen complex. But even if you go to modern materials where the boron-oxygen complex is so-called deactivated, you still got quite strong injection dependencies of your lifetime. So what does that mean? When you go from VMPP to VOC, your injection density increases quite lots, and with that your lifetime increases, and with that your J naught decreases. And remember that curve where we had a high J naught at lower voltages and a low J naught at higher voltages? We got the kind of bend of the blue IV curve I draw by hand just a few slides ago. And you see it here directly on the simulated current plots. Just look at the base. The base is the green line here, how it bends down. It doesn't go straight up. And that bending down was the main reason why the fill factor was lower, and not RS, as you would just think of, when you think of just textbooks without really addressing the ideality factor. So it's basically an ideality factor problem. You would actually notice just by normal IV curve analysis I showed you at the beginning. If you do that quite systematically, like at the beginning, with IV curve analysis, you notice that without any simulations. But I show you here the simulations because the dynamics, in a way, becomes apparent. Huh? So it's the ideality factors that causes the low fill factor. Though, when you got two cells with a low fill factor, and the main reason for the low fill factor is RS, then the pseudo fill factor, after correcting the IV curve with RS, is close to the unity fill factor. But if it's mainly something recombination stuff happening, like a saturation mechanism, then the pseudo fill factor stays quite far from the unity fill factor. And this is a good indication of which direction you should head in improving your cell. Let's look at the most recent example. Industry at the moment is in transition to go from standard cells to PERC cells. And there are quite a few companies who already did that transition. And it's hard work. And it kept us in our simulation group very busy. So we actually could survive the crisis by helping people analyze the cells to go on PERC cells. And this is an example not from a company because they're very protected about it. I mean, I couldn't publish it. This is just examples from a roadmap we are going to publish at the European PV conference in September in Hamburg. And let's say that's an initial cell where the emitter dominates the losses. And the base is quite far down, and blue here is the rear diffusions, and lilac is actually the surface at the rear. And at MPP, here it's always the losses given at MPP are dominated by the emitter. When you improve the emitter, the red curve shifts down. And so that also shifts, of course, the losses into the base and the losses into the back, because your excess carrier density increases when you got a better emitter in the base. And that really affects, of course, the other device parts. And what you see is, okay, an improved emitter in this case gives you an improved fill factor. People manage to do that, and not like in the last example. So I take this plot just to here, and we go on. We say, well, now we improved the emitter, but look at that mess up here. And we should actually improve the rear and the base. And this, what it's done here. You see it's only the green curve, the base, that comes a bit on top of the emitter. It's not quite dominated by the emitter, but both are important. I mean, it adds, So you see, okay, also I improved the base material, the recombination losses actually, and the base stays the same. And why? Because it improved the rear. And that gives you higher injection density in the base, and that gives you more losses in the base. And the fill factor increased, but look at that. I mean, this is an internal fill factor with very little metallization. It's not really lots, is it? You would expect a higher fill factor if you do that. So what you can do, instead of just improving the rear and the base, like, that's the same example as previous slide, you improve the base again. And now the emitter dominates again. And because the emitter behaves quite nicely, goes up in a straight line, then you get the real improvement in your fill factor. So that cell got rid of all these kind of, not all, but most of the influences from the base and the rear. And that's why you got quite a big increase in fill factor compared to the previous ones. Yeah? So designing a PERC cell is basically a very intricate kind of juggling between the losses along MPP here. And that determines your roadmap of a PERC cell, of what you should do next. So just as a very last example, I want you to actually point to one nonlinear phenomenon. We improved the initial emitter to here. And then we didn't improve the emitter anymore. We kept the emitter exactly the same in those three examples. But look, the losses in the emitter increase. Also, you got the same emitter. Your emitter gets worse and worse and worse, the better your PERC cell is. So why is that? And the reason is, when you improve a PERC cell, your VMPP, your maximum power point, actually improves. Look, that red line here, this is the losses in the emitter, is nearly exactly the same as that red line here. But MPP is higher, and the losses increase exponentially. I mean, this is a logarithmic plot, don't forget it, huh? So you got an exponential increase of recombination losses when you improve your cell due to VMPP that increases. And that's why when you optimize a PERC cell, you should think of, okay, when I improve things, I don't need to improve the base so much until the emitter dominates, as I actually would think from here. From here, I would think if that stays the same, the emitter, I would need a very, very good base till the emitter dominates. But actually, the emitter does quite a bad job. And so you don't need to improve the base as much as you would think linearly to have a PERC cell that has a high fill factor. So I hope, just as a last thing, that this would give you a bit of an insight of how useful simulations are in designing an optimum roadmap for your PERC cells, because you won't do all this just by intuition. I mean, hardly anyone has intuition to do that without simulations and think, it's this, it's that. It's often people just tapping in the dark really and trying all kinds of different things to improve the PERC cells. But this gives you a strategy to improve it. And it's a strategy to improve the notorious low fill factors of PERC cells. I mean, people are often very happy to have fairly moderate fill factors in PERC cell production compared to what you would expect from Martin's equation. So my main points are, I recommend you to do a very detailed extraction of the series resistance as a function of voltage when you look at your experimental IV curves. So you see a clear distinction between resistive losses and recombination losses. Don't mingle them up with just taking some rough kind of estimates of RS. And then when you work with these properly corrected IV curves, you can really do a proper detailed fill factor analysis and see what's the main reason for your low fill factors. And for further analysis or further predictions, I have found simulations very useful and really a task that's worth doing. And if the fill factor is not only determined by RS, it's also determined by your recombination. Thank you very much for this lecture.
question?
Yeah, it's very nice to have these curves, colored curves for the emitter and for the different recombination channels in theory, but can you comment on the best ways to actually extract these different recombination dependencies for the various parts of the cell experimentally? So if I have a cell and I want to find out what are those curves for that specific cell, how do you measure those? So if for an actual cell analysis, I measure my fill factor is 80%, and I want to find out now, is it the pink curve, is it the red curve, or is it the blue curve? How do I actually address that?
Well, this is I would say my economical niche, that people haven't come up with a good experimental method, so they resort to simulations to do that. But I would say photoluminescence may have a good potential of assessing lots of that. I don't know whether people do it so directly and whether they do it voltage dependently. No, the advantage in simulations is you get a voltage dependent picture of things. So you would also need probably, it would have an advantage if you wouldn't just do a PL analysis at MPP, but actually voltage dependent to see a dynamics.
Yeah, of course. But if you have a lifetime, for instance, an injection dependent lifetime curve, you can basically plot that curve for the base, the green curve.
Well, if you know the injection dependent, if you know the injection density in the cell, but that's what you probably know via PL then, yeah.
Now, if you take a lifetime measurement on a wafer, which is well passivated and all that, and then you can characterize your base material. But I'm just wondering, all the other very detailed recombination channels, how do you assess those?
Well, we assess those by always etching off a fabricated cell, repassivate it to measure the lifetime of the base material again, because that of course depends on gathering whatever. That's a very important parameter for us in simulations. Otherwise you always can use the base to compensate for all some errors you do in your simulation. So you shouldn't do that. You should really know your base well. The emitter, I don't know. I mean, the emitter may be possible with photoluminescence, it may be possible. No, it's hard to experimentally, it's hard to divide a cell into different regions, isn't it? It's you always get a kind of a lump thing, and you need an analysis to kind of subtract one from the other. Like when you do a QE analysis, people sometimes do a QE analysis, but be aware. I mean, in PERC cells, the losses at short circuit are not the same as the losses at MPP. It may even switch. I mean, the emitter may be quite bad at JSE. You may have still quite lots of losses in JSE because of your selective emitters, say. But when you go to MPP, your base may just overtake the emitter, and you're actually limited by the base. And that's why in high efficiency cells or in PERC analysis, you quite rarely find that people do an analysis with the QE, with the quantum efficiency. And the quantum efficiency actually is able to discern, losses that are in the blue part in the emitter and losses that are in the red part in the back of the.
Yeah, but I mean, still, if I say I switch your red curve with your green curve, and I get exactly the same result, but it has probably no basis in terms of reality in my cell. So I'm just wondering, how do you get to those curves that you input in your simulation?
Well, I mean, we look, of course, at the doping profiles. That's very important to know the doping profile correctly. We measure J0 of our diffusions with, and you need to be careful with doing that. I mean, the Kane-Swanson method that's usually applied for extracting J0 usually underestimates J0. This is just because don't think that if you have a symmetric sample, that your sample is operating in a symmetric way when you measure J0 with the Sinton box. There's nothing wrong with the Sinton box, nothing wrong with the method, it's just the limit of that method. And we published a few papers about that, how to extract J0 as well as possible. So we do that, of course. We always etch back the cell so we know the base. We look at microscopy, SEM pictures of local structures at the back surface field, of the local back surface field. And then, when we are able to simulate the ideality factors, as I showed you, we do in the first go a prediction of change this, change that. People go to the lab, do it. And if the predictions are correct, we start trusting our model, only then. Only then. So ideality factor is quite nice. We are already happy because we are often very close then, but you always just trust simulations after the first feedback round. But I can't really answer your question satisfactorily. I mean, this is an area to work on, to do it experimentally instead of with simulations.
Yeah. Thank you for the information. It's very interesting. I'm wondering whether in the ideality factor is where everything is hidden. So once you extract that voltage-dependent series resistance, that resulting ideality factor is really not the ideality factor of the diode, but the fact that the J naught is changing, right? Mm-hmm. So isn't there, if we know that the ideality factor should be 1, then we could figure out how the J naught is changing to give us the ideality factor that we measure. Yeah. And then from there actually be able to build this.
I find the RF, the properly corrected IV curve very important for the understanding, and this is done purely experimentally. But I mean, let's assume an emitter, and an emitter has quite a high sheet resistivity. You got a different injection level between the fingers and towards the fingers. And for a given J naught, you actually increase the recombination losses, because the losses in the emitter are not only a function of J naught. For a given constant J naught, they're a function of the local voltage along the emitter, of how you operate that junction. And this is actually what's often causing confusion about J naught, about saturation current. I mean, there are people that say we shouldn't even call it J naught. I think we should call it J naught. We should only make a distinction of how I operate locally such a diffusion, instead of thinking that J naught is all kind of wrong. And when you look at such an emitter, that actually also leads to a different ideality factor. You know what I mean? So it's not only the base, it can be quite a high resistivity emitter also has such effects, just by recombination, apart from the resistive effect. And I haven't come across another way than, I mean, people these days have very good analytical theories. You don't necessarily need to do numerical simulations, but somehow you need a theoretical understanding of what's happening when you see such an IV curve. Does that answer your question?
Yeah, it does.
Yeah. Any other questions?
No. So let's thank Pietro again for the great talk.
Yes, thank you. Thank you very much. You're a very nice audience.